Okay, let's start with section 3.1 for this screencast. So the objectives here are going to be to find the slope of the tangent line to a curve, slope being how steep it is at a certain point. For example, here it's horizontal, so the slope is 0, here the slope is negative, and here the slope is positive. The second objective is going to use the limit definition to find the derivative of a function, as you have seen in pre-calculus, and then understand the relationship between differentiability and continuity. So, a few things that we want to address first about tangent lines. There's some ideas that we need to break. This is a tangent line that we would all be able to sketch. Some students tend to think a tangent line by definition does not cross the graph. Like here, this is a good example. It's a tangent line, it doesn't cross the graph. However, this does not always have to be the case. For example, here, this tangent line actually crosses the graph. And in fact, this example here as well, this is the tangent line. So in this neighborhood of P, yes, it's true that it doesn't cross the graph, but somewhere down the road, there is an intersection. So just to say that a tangent line is a line that doesn't cross, that touches without crossing a curve is incorrect. The definition of the derivative with its mathematical formula is written here. You have seen that in pre-calculus. So we say f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So we've discussed that this is actually rise over run. So it's the first time here that we use a concept from Algebra 1, but kind of push it beyond because we add the idea of limit. If f prime of x exists, then we say that f has a derivative, or we can say that f is differentiable. For example, using the formula, we can try to differentiate f of x equals x cubed plus 5x. So remember, x represents a number. If it was something else like f of a circle, it would be circle cube plus 5 circle. But the circle that I'm talking about here would need to represent a number. So whatever you put in this parenthesis, you put it here as well inside a parenthesis and here as well. That's why f of x plus h, represented here, is x plus h cubed plus 5 times x plus h. So f of x plus h minus f of x all over h, and we take the limit as h approaches 0. If we expand all that, we get this long fraction here, and things start to cancel out, which obviously is what we really hope for. We really hope for that because if we start by plugging in h equals 0 at the beginning, meaning in this row here, we would get 0 over 0. That doesn't give us an answer. So by expanding, simplifying, we are hoping to reach a point where it is possible to plug in h equals 0. This is called direct substitution. So up here, direct substitution is not possible. If I just plug in h equals 0, I get 0 over 0. But after simplifying, and simplifying more, I get to a point where I actually have a polynomial here, and I can plug in h equals 0. So that's the step that is the most satisfying. If h equals 0, what is left over? Well, 3x squared plus 5. And that's the derivative. So if you pick at this point any value for x, f prime of x will give you the slope of the tangent line at that point. So f prime of x equals 3x squared plus 5. There's a variety of ways we can write the derivative, f prime, y prime, dy dx, ddx f of x, df dx. So a little application here, which will bring up the second important concept that we take from Algebra 1 and use a lot in AP Calculus. Find the tangent line to the graph of f of x equals 2 over x at the point 2, 1. So we are looking for a line. It's a tangent line, but it's a line. And when we look for the equation of a line, we need two things. We're going to do that 50 times this year, so you really need to remember that. To find the equation of a line, we need a point and we need the slope. It's always these two. Now, if you remember from Algebra 1, there's other two things we can have in order to find a line. For example, if you have a point and another point, then with 2 points you can also find the equation of a line. Or maybe you have the x-intercept and the slope. So these two things also allow you to find the equation of a line. In AP Calculus AB, it's virtually always going to be you want a point and you want the slope. So the point is given, we have it, it's right here, 2, 1. And the slope, well, perfect. The slope is exactly what we were talking about above. The slope is going to be f prime at x equals 2. So to find f prime of x, I use the formula, the definition of the derivative. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. This is what it becomes when I plug in f of x equals 2 over x. And again, I'm going to try to cancel things out. So the first step here is that this numerator, I want to put it with the same denominator, mini denominator at the numerator if you want, the same denominator as x plus h times x. And by cross multiplying, I'm sure you know how to do that, this is where we get, and the 2x simplifies. So that's awesome, but what's even more valuable is that after we do that, the h's cancel out. So the h at this numerator cancels out with the h at the denominator. After that, after we proceed to rewrite the expression without h, we can try again to plug in h equals 0, and we see that this time it works. If we had done it from the beginning up here, it would not have worked. If you try h equals 0 here, you will find 0 over 0, which is always a problem. So here, we can plug in h equals 0, and there we go. We find that f prime of x is negative 2 over x squared. Therefore, we are interested in the slope at x equals 2 precisely. The slope is negative 2 over 2 squared, which is negative 1/2, right there. So, the equation of the tangent line is y minus 1 equals negative 1/2 times x minus 2. From Algebra 1, you've also learned many ways of writing the equation of a line. This one, if you're like me, was not your favorite, but it's going to be the one you want to use in AP Calc because it's immediate. Because we always start with a point and a slope as our goal, this point-slope form is just the easiest one to get the answer that we're looking for. So you want to just get used to only writing that. You don't need to distribute, you don't need to isolate y. We're happy with this answer. And the more you do it, the more you'll be comfortable. So I encourage you to start right away by using the point-slope form. You'll be comfortable with it sooner. There's another way to write the derivative, which is, again, rise over run with a limit, but this time we introduce a c. It's the derivative at c when x approaches c. So I made a little sketch that I want to show you for this situation. So I just took a picture of my whiteboard. You can even kind of see me here. So here's what we did together with f of x and f of x plus h. This is the situation, the way it would look like if we use c and x instead. So for this alternate definition of the derivative. This is a secondary definition that we don't use so much, but we use sometimes, including in this section. So we would call this c, we will call this x, and then that means this is f of c, this is f of x. And you can see that now we're looking at the limit when x approaches c. And if you look at the sketch at this point, when x is far away from c, you can see that the secant line has a positive slope. However, as x approaches c, if in your head you can visualize how the secant line would progress as it approaches the tangent line, it will reach a point where the slope is negative. Okay, so why are we introducing this alternate definition of the derivative? Well, the reason is if we want to look at the derivative from both sides, from the right and from the left, it's much more easy with this definition instead of the other one. So why is that? We can define x as approaching c from the negative side, or we can define x as approaching c from the positive side. This is a little bit of an advantage. In the original definition, we just assume h was positive, I guess, but here it's just easier to visualize. So we put a little minus to say c is approaching, so x is approaching c from the negative side, from the left side, and here x is approaching c from the positive side, so from the right side. Minus is on the left and plus is on the right, just like when you draw the number line. So we will want to do these one-sided derivatives or one-sided limits because sometimes the derivative is undefined. In a case like this, we say that the derivative is undefined at x equals 2 because there's a sharp turn. We can express that more mathematically by looking at both one-sided derivatives and seeing that they are different. If the one-sided derivatives are different, then the derivative does not exist. If they are the same from the left and the right, then the derivative exists, and the derivative is equal to that number. So in the example here, without calculation, determine the one-sided derivatives. If we make the sketch of f of x equals the absolute value of x minus 2, this is what we get, and we realize this part of the graph is y equals x minus 2, so the slope is 1. On the other hand, this part of the graph is actually the graph of y equals negative x plus 2, so the slope is negative 1. Therefore, from the left, the derivative would be negative 1. From the right, the derivative would be positive 1. And given that these two values do not agree, we say that the derivative at x equals 2 does not exist, because the one-sided derivatives are different. What does it look like if we have an algebraic situation? So here purposefully I did not sketch the graph, but I'm sure you can sketch the graph of y equals x squared for x negative and y equals 3x for x positive, but here on purpose I didn't sketch the graph. So from the left we would have the derivative f prime of 0, so the derivative at x equals 0 is the limit as x approaches 0 from the left, and here is the expression. So because we are approaching 0 from the left, this is the trick, this part here, because we are approaching from the left, it means we are actually reading this rule, right? So f of x is 0 plus x squared minus f of c, which is 0 squared, over x minus c, x minus 0. So we can simplify that, and at this point, after cancelling out x's here, we get the limit of x, and now we can plug in without any problem, and we get that from the left, the slope is 0. If we arrive from the right side, so because of this plus here, now f of x is going to be positive. So we have to read this rule. So f of x is actually equal to 3x now. So 3x minus, this is 0 squared, because when c is 0, it's the top rule. Over x minus 0, we have 3x over x. X's simplify, and therefore, after direct substitution, but there's nothing to substitute in, we get that the slope from the right is 3. So there's a problem. The slopes disagree. On the one side, on the left side, the slope is 0, and on the right side, the slope is 3. Therefore, even though that was not the question, we can conclude that f prime of 0 does not exist. So this is going to be a terrible graph, but this is the parabola from the left, and then from the right, it's a line that has a slope of 3. So we can see that at x equals 0, there's a sharp turn. So the final note is something I said several times, but it's crucial. If the one-sided derivatives are different at x equals c, then the function doesn't have a derivative at that point. Situations where the derivative fails to exist. There are 3 categories. First is if there's a discontinuity. So for example, here at x equals 2, but also at x equals 1, x equals 0, let's say at x equals 2, the graph is not continuous, so the derivative does not exist. Secondly, what we just saw, if there is a sharp turn, the derivative does not exist. Sometimes students use the word cusp for that, which is tolerated, but it's better to say sharp turn. And finally, if we have a vertical tangent for a split second, or for an instant here, the slope is vertical, then the derivative does not exist. So you could say that the derivative is infinity, but we just, when something is infinity or negative infinity, it's not a number, and in AP Calc it's just a blanket statement that the derivative does not exist. So last 2 things. Firstly, the theorem here, differentiability implies continuity. What does that mean? It means the following sentence here: if f has a derivative, then f is continuous. Okay? So sometimes in more abstract questions in AP Calc AB, they would not tell you that a function is continuous, but they would tell you that f has a derivative. If they say that, then automatically you know that it's also true that f is continuous there. There can't be a jump if there's a derivative. On the other hand, the converse is wrong. For example, so what is the converse? The converse would be, if f is continuous, then f has a derivative. That is not a true statement. For example, if you have a sharp turn, this is a continuous function, but it is not differentiable here, as we saw earlier. Finally, using your TI-Nspire to find derivatives, here's a simple example. There's 2 ways to do that. If you want to find the derivative of f of x equals 8 sine x, at x equals 5, so you're interested in knowing what the slope of the tangent line is for this graph, then you have 2 ways of doing it. Either you're in the calculator part, and then you click menu for, so when I put a square here, it means it's the key, you just press the number 4. So you press menu, you press 4, you press 1, and then you do ddx. You just make sure that this comes into your calculator, enter, and it'll give you the value out. And in AP Calculus AB, you always have to round to 3 decimals or more, but at least 3. So 2.269, you can either truncate or round. The other option with your TI-Nspire that I invite you to try as well is if you're in the graphing part of the calculator, then you press menu 6. So firstly, you would need to type what the graph is, but you press menu 6, then 5. Why 5? Because we're looking at the slope at x equals 5, and it'll give you the value as well. And again, 3 decimals. So that's it for this section 3.1. Thank you for listening.